Alright, this is a video for section 4.1 for business calculus, and this chapter we're going to talk about exponential functions and logarithmic functions and how to deal with them in calculus. So for this section, we introduce exponential and logarithmic functions, which are two of the most useful functions in all of mathematics, and we're going to develop their properties and apply them to a wide variety of problems. So first off, recall what a exponential function is. So we're going to begin there and show that they can be used either for an exponential growth, okay, where we're increasing, or an exponential decay where we decrease very rapidly, okay? We're also going to define the very important mathematical constant E. So first off, exponential functions are a function that has a variable in the exponent. So such as f of x equals 2 to the x. The bottom, that 2, is called your base, and the x is called the exponent. Okay, this works for any number, okay, and we're going to focus on positive numbers because that's the only way it works for an exponential function. So for any number a that's greater than 0, a positive value, the function f of x equals a to the x power is called an exponential function with base a and exponent or power x. Okay, so you can have f of x equals a to the x. That a is your base and the e is your exponent. Now, what does that look like if we actually graph it? And the graph will actually help us see some patterns as we go through different problems. So on slide 4, it says the table below shows some values of the exponential function f of x equals 2 to the x and its graph. And these are based on these points, is shown on the right. So here they've got the function f of x equals 2 to the x graphed, and they picked several x values. You could use any x values you want, doesn't matter, but these are some basic x values that work. And then by plugging that x value in, we'll of course get our y values that we could graph. All right, and what you're going to see is this function's on the left-hand side of the graph starts out really small, and then it grows very, very quickly. All right, our domain ends up being all real numbers. I can put any x value I want into that function and it's going to work. But the range is only from 0 to infinity. We see as that x value gets very small, the negative exponents, we're getting fractional answers for our y value, and it's getting increasingly smaller. Okay, increasingly closer and closer to 0. But we're never actually going to hit 0. So our range is from 0 to infinity. We have a horizontal asymptote at the x-axis. All right, and again, we're increasing. So as we get larger, as our x values get larger, so do our y values. So it's an increasing function. Now clearly, the exponential function 2 to the x is quite different from the parabola x squared. Okay, so you don't want to get those two mixed up. They're very different. But in particular, it is not symmetric about the y-axis and has the x-axis as a horizontal asymptote, meaning that the limit as x approaches negative infinity, or the limit as x approaches negative infinity of 2 to the x is equal to 0. Okay, remember that's what our horizontal asymptote means. It's the limit as x approaches negative infinity of the function goes to 0, or the limit as x approaches positive infinity of a function is going to 0. That's the definition of a horizontal asymptote. All right, so the first function showed an increasing function, and that base was 2, okay? And it was greater than 0, or not greater than 0, greater than 1. What happens if we have a base value that is between 0 and 1? So in this case, 1/2 x. Well, what happens if we have that 1/2 x, okay? It looks the same basic shape, but it's flipped over the y-axis. And we see that we're starting out very large and we're decreasing down to 0. The range, or the domain, is still all real numbers from -infinity to +infinity. That doesn't change. And our range is still 0 to infinity. That's not changing either. Okay, but this one is a decreasing function. So what can that tell us? It says we can define any exponential function, f of x equals a to the x, for any positive base a. Okay, again, that base a has to be greater than 0 or this does not work. And we're always going to take the base to be positive, so for the rest of the section, the letter a will stand for a positive constant. Again, if it's not positive, this doesn't work at all. All right, so looking at that, here's some hints to help you as you're graphing or to know what type of values you're going to have. If your base is greater than 1, okay, so y equals a to the x with a greater than 1, it's an exponential growth function, and all those slopes, okay, if we did all the slopes of the tangent line hitting that curve, it's going to be positive, and they're all going to slope upward. If the base is between 0 and 1, okay, so less than 1. And again, remember, they've always got to be positive, so that a value is between 0 and 1. It's an exponential decay function, and that's going to work every single time. So if your a value is greater than 1, you have an exponential growth. If your a value is between 0 and 1, or less than 1 here, you've got exponential decay. All right, let's keep going. Now, where we're going to use this the most for business calculus would be money cents. Okay, we're going to use this a lot with money. So the first thing we can talk about is compound interest. So money that is invested at compound interest grows exponentially. Banks always state annual interest rates, but the compounding may be done more frequently. So for example, if a bank offers 8% compounded quarterly, that means each quarter of the year, okay, remember quarters 4 parts of a year, you get 2%, or 1/4 of the annual 8% interest. So that 2% of your money is added to your account each quarter. If you begin with P dollars, okay, so that's the principal, some amount, at the end of the first quarter, you would have P dollars plus 2% of your original money. Okay, so that's P plus 0.02P. And that's the value after 1 quarter if you have 8% compounded quarterly. So notice, there it goes. Notice that increasing a quantity by 2% is the same as multiplying it by 1 plus 0.02. We see that right here. P plus 0.02P is equal to P times 1 plus 0.02 if we factor out that P. So since a year has 4 quarters, all right, T years will have 4 T quarters. Okay, 1 year has 4 quarters, so T years will have 4 T quarters. Therefore, to find the value of your account after T years, we simply multiply the principal by 1 plus 0.02, a total of 4T times. All right, so we have the principal times our 1 plus 0.02, 4T times, however many that needs to be. Well, this entire part here, instead of having to write it out 4t times, it's just the formula 1 plus 0.02 raised to the 4t power. This should look like an exponential function. All right. So let's keep going. If we do this, what happens is the 8%, which gave the 0.02, that's 0.08 divided by 4, it gave the 0.02 quarterly rate, can be replaced by any interest rate written as a decimal, and the 4 can be replaced by any number m of compounding per year. If you remember back from college algebra, a lot of those formulas for compounding or times compounded per year, it was usually an n. So if you want to replace m with n, that's fine. Okay? But the formula becomes the value after t years, that final amount, a lot of times that'll be called an A, is P times 1 plus R over M, all raised to the MT power. All right, here's a formula for you. I'm going to do A instead of value after T years is equal to P times 1 plus R over M, all raised to the MT power. Now, to remember some common M values, monthly compounding would be 12 because there's 12 months in a year. Daily compounding would be 365 because there's 365 days in a year. Quarterly was M equal to 4. Semi-annually would be M equal to 2. Weekly would be M equal to 52. Okay, those are just a couple of the common ones. Now what I want you to do is to look at example 1 and work it out, and then we'll come back and check your work. Okay, what you're doing is taking the information that you have in example 1 and plugging it into the formula. All right, so take a second and try to work that. All right, so by plugging into the formula, or as we read the problem, find the value of $4,000 invested for 2 years at 12% compounded quarterly, gives us a P of 4,000, T of 2, 12% gives us R as 0.12, and M is equal to 4. Once you have all the numbers identified, this is a fairly easy problem because all we're doing is plugging the numbers in and then plugging things into our calculator. As you're plugging this into the calculator, always take care of the inside of the parenthesis first, and that'll help you save a lot of issues on your calculator. I do several steps to plug all this in. At the very end, you should get $5,067.08. Since we are talking about money, you will always round to the hundredths place, 2 decimal places, because money always has 2 decimal places. All right, we're going to continue on in the next video.